And we are back already from yesterday. Hey guys, welcome to another episode of Ferris Makes Demos. This is SNES Kefrens Bars 2, which was not something I expected to do today. But after trying a bunch of stuff yesterday and having that not go so well, I was thinking that I should, give this a shot again today, because this was actually pretty fun to work on. And I thought of a new strategy that should actually work when I kind of think through all the different possibilities of how this will go. This will work. Local hoster Ferris and Natural Light, that's a new one, yeah. Yeah, I actually tried to let more of it in than usual. So, like, my window's open, so if there's some extra noise pollution, sorry about that, but it's really going to make my experience a lot better. Cool. Yesterday we started working on this Kefrens Bars stuff. Whoops. Showing my OBS there. And basically just failed with a bunch of different attempts. Actually, let me check out what I had yesterday. So this is what I left off on yesterday. There we go. By the way, hi to guys in the chat: Dino Collin, Pelicus, Arthur Carlson, and local hoster. Glad you guys can make it to part 2 of this journey. But basically, I was trying to, based on like raster timing, I was trying to change these registers from the CPU to create this effect, including updating VRAM. And it looks like that's really a bad idea for this hardware in particular. So we're going to take a different strategy and do something HDMA based. So the first thing that I thought to change was, okay, let's change our scroll registers to get this stretching with HDMA. While we're at that, we can actually probably try to use the HDMA to fire off the DMA writes that we were doing. So I was thinking, I looked at how many master cycles you have in the DMA period and how many cycles DMA would take to transfer a small amount of bytes. So if I dropped the number of tiles to like 16, which is like half the screen, which would be more than enough for this effect, it ends up being that you need to update 32 bytes. And I looked at the DMA registers, and it turns out that you can have it so that you write a word, so you write a 16-bit value, and then internally you can have the pointer increment by 64 bytes rather than like by 2 bytes. And if you space out the character graphics in memory, so you display every 4th tile rather than every first tile, so you go, instead of 0, 1, 2, 3, 4, you would do 0, 4, 8, 12, 16. Then that writing, you would actually be able to like have a contiguous block in memory that then you upload to the GPU just by setting these registers, and it would update the first 2 lines of every tile, which I thought was kind of a neat trick, because then we could sit there and change the data on the CPU, still in tandem with the raster, but then in HBlank have it upload all that data every time. And even though the numbers should have like made some sense, what I found was that you actually can't trigger DMA from HBlank. You can only do it from VBlank or FBlank, which is your forced blank, where you basically shut off the screen. So that was a bust. Although I did get a couple things out of it. So let me check out the master again here. What I did get out of it is that uploading of the data actually does work. This is actually every 4th tile now, but you can see we still have our red lines at the top. So that actually does work, but I think I'm actually going to revert that. Also, I am uploading that with DMA, but I'm doing it from, in this case, I was waiting for VBlank and then doing it here, rather than doing it in tandem with the raster, which I've commented all that stuff out. And then I started adding back a VBlank handler here, which I'll get to why in a sec. So now what I'm thinking, though, is that the original effect only really has to, like, every scan line, it has to do a read, modify, write. Now, the read is going to be the problem, because we would have to read the data and then modify it and then write it all within that HBlank period. But if we keep a local copy of the chars in RAM like we were going to do anyway, then all it actually is we're just doing a write every scan line. So I'm thinking that every VBlank, we can fire off HDMA, which is basically the same as a copper list on Amiga, but a lot worse. Fire off HDMA into these channels, and then we can just fill in the data and the positions that it'll write. So we'll have one HDMA channel that's going to update the scroll register, so that'll give us our stretching. We'll have another one that's going to write out the target addresses for where we're going to write to VRAM, and then we'll have a third one that's going to write the actual data that we're going to write in VRAM. So each one of those lanes, the first lane that updates the scroll register, that's going to write 2 bytes each time. The second one's going to write 2 bytes each time to write the address, and then the third one's going to write 2 bytes every scan line to actually write the data. And so then our job is from the CPU, from VBlank basically, or at least in our VBlank handler, I should say, to actually populate those tables. And we're totally allowed to populate those tables while they're being read, as long as, of course, we're ahead of the data that's being read. That should actually work just fine. So what I want to do is I want to fire off HDMA from those tables and then write the tables right after we fire it off, so that we have as much frame time as possible to be able to do that. So with all of that, so our update loop is basically going to read, modify, write into memory, but it's going to read, modify, write into memory, and then schedule write via the HDMA channel. Daniel Collins says, can you double buffer the data? I don't. Well, other than the fact that we're going to also read, modify, write in memory, I don't think that'll really help too much. I guess we could double buffer the HDMA channels. That should work, if that's what you mean. That could work. I don't think we'll have to, though, because I think we'll be more than fast enough to just keep ahead of the pointers. The hard part with timing here is not that we didn't have enough time. I think it was just that we couldn't get accurate enough time. But by using HDMA, that will solve all the timing stuff for us, and then we just have to make sure we update these tables within a frame, and that's a lot of time. So, I think this will work pretty well, and it's a strategy that should play a lot more nicely with the hardware. But first, what I'm actually going to do is I'm going to rearrange the data again so that we have it in contiguous tiles. Because that'll make the scheduling a bit easier. Oh, that got sunny. My camera is not calibrated to natural light, so I'm going to look really washed out, but I don't want to enable auto white balance because then I get really low frame rate and stuff, so I'm not going to do that. Okay. So all I did to actually change that data is there's one of the bits in the way that, so this register here, 2115, it determines how you actually access the video memory. Like when you're writing data to it, how does the internal pointer increment? And if this is 0, then you increment with 2 bytes every time it increments. This is 64 bytes, and then there's 128 and something else. I can't remember. Anyway, if we just set this to 0, then we're going to be writing contiguous memory. So if I run this just as is, we'll just get all of that data written to the first tile, which in this case is probably fine. Or I guess that kind of becomes a problem if we want to upload this all at once like this, because then we would have to also upload the data in between. Maybe I'll just keep the data as is, actually. And then we can just change the pointers we write to. That's actually probably fine, because then we can just upload this in one go, which is nice. Because particularly in VBlank, we have to clear the data, so clear our local copy. And we need to clear the local copy and then clear VRAM. I mean, we could have done this in a loop where we just clear the specific bytes, but it's easier and faster to just do DMA like this. The way DMA and also HDMA works, by the way, is you have a set of channels. And you can basically queue a bunch of these up, and it will try to do as many as it can in parallel. But basically, you have 8 channels, and you set like this is, I can't remember what the one bit here is. I think it's the access pattern, like how it actually will write to this register. So this is the access pattern. This one is which register you're writing to. So the DMA works to and from these port registers rather than to and from like VRAM directly. So if you imagine this as being 2-1, whatever the value is in here, that's what you're writing to this register, and that's the port that it will write to. This, depending on this, you can have it like increment the this value between each write and stuff, but not very useful for us. And then, like, I think this will write one value every time. This will write a 16-bit value every time, for example. So that's what we're doing. Or we're writing 2 bytes to the same register. And then, or maybe it's this one in the register plus 1. I can't remember the exact bit combination here, but it works. Then this is the address. Or this, actually all of these 01, 02, 03, and 04 are the address. By the way, for different channels, you would do 4311 or 4321, and then all these registers act the same, up to 8 channels, so 0 to 7. But yeah, so this is setting the low byte of the address, the high byte of the address, and then the bank, or sorry, low byte, here, yeah, low byte, high byte, bank, so all 3 bytes of the address there. These two, oh yeah, this was actually not related to the DMA in particular. This was actually writing the I'll actually put this up here. What this is doing, this is just resetting the VRAM address to the first address, so that when this is going to write to the right port of the VRAM, that it's actually going to start from 0. So that's what this is doing. So it's separate from the DMA burst, but it's related in the same way that configuring the write ports here is related as well. So we configure the write ports, then we set up the DMA. These last 2 things are a 16-bit amount of bytes, which we only need 32 bytes, and then the high byte's 0, so we set both just in case. And then when you're ready to actually fire them off, you load a bit mask into one of these registers, 420B for regular DMA, 420C for HDMA. Now in this case, regular DMA is just going to take like flat arrays from here and then upload them to VRAM or take them from VRAM. Of course, HDMA is going to work a little bit differently, where you have, instead of pointing to raw data here, you actually point to this like run length encoded table format, and it's able to actually read those. I actually am going to fix my camera, by the way, because I look crazy right now. Just turn on the auto white balance stuff here. See if this helps at all. Nope, still super bright. Just fix my exposure by hand. There we go. That'll do for now. Also, I can do PewDiePie zooms. Whoa! Lookalister says, you have the driver installed in Norwegian? Yeah, a lot of my stuff ends up being Norwegian, because I can't remember why, to be honest. I think it gives you, like it goes off of your Windows settings. And I ended up with Norwegian Windows because, I don't know. Look, also DMA explanation appreciated. Yeah, no worries. It's important to understand, to see what I'm doing, and also for me to understand. Like, I need to explain it again because it's been so long since I worked with this stuff. Most of the stuff that I did actually for the Elix demos was actually work with the DMA, because that was by far we were uploading data mostly is what we were doing. So by far, this was the most common kind of things we were doing. But I always forget the registers because, like, especially in that scenario, like I set up those routines once and then never touched them again. So kind of typical. Indeed, rubber duck debugging, rubber duck explanation, rubber duck anything. It all works very well. Yeah, so let's set up, start working with the HDMA. The first thing I want to do is set up the stretching loop. I call it the stretching loop again because I'm thinking in other system terms, but just the thing that'll display the same scanline over and over again. I'm going to keep this, by the way. I did also change this to use the first 16 tiles rather than 32. I'm going to keep it that way for a couple reasons. One, I actually kind of like it for debugging, because if we get like a whole red screen, we can tell that it is, like, it'll just be red on one side, which will give us some kind of context to Yeah, show us what the rest of the screen looks like. I don't know. It makes more sense in my head. It also keeps the data down a little bit, so this should make a lot of sense. We'll keep that, and then we'll, set up the HDMA for the scroll register. So I need to look up how to do the HDMA tables. Because I totally don't remember how to do this. As far as I know, though, it's just like you have like one for each entry. You have like 1 byte that determines how many like it's like a hold value. So how many lines this value will hold for, and then the data itself. But I can't quite remember because there may be other like bit masks and stuff in there. And here we go. I found what looks to be some email correspondence. Yeah, another thing about the HDMA is it has multiple channels, but when you're doing HDMA in particular, the channels actually go sequentially. So like the lower number channels take precedence over the higher number channels. And this is very useful in this case because we're going to update the scroll register, we're going to update the VRAM address, and then we're going to update the VRAM. And the VRAM address has to be updated before we write to the VRAM. So that's going to be important. Hey, Studio C, how's it going? Also, hi, AMX. Yeah. Okay, so it actually is very easy here. We just write the number of times to repeat the next word, which in this case is always going to be 1, and then the value. And eventually we have byte 0, which will end the list. So that should be really easy. So let's start by making that table. I'm just like kind of placing these tables randomly in different parts of memory, but we'll do somewhere really far off. Because I mean, each one is gonna, like, we're gonna need 224 values by 3 because we're gonna have the repeat value, which is gonna be 1, and then the word value, and then plus 1. So 673 bytes for each of these, which is going to be 2A1 hex. So if I make it like each of these a kilobyte apart, then it should make sense. Something like this. So we're going to need the scroll HTML table. We're going to need the adder. And then we're going to need the VRAM data. And I think that's all we need there. Now, one of the things that you could do if you're really concerned about speed is set up like the templates for the table. So like you could set up the repeat values and then just write in the data every time. I'm actually not going to do that because I don't think we have to. I don't think we'll need that for speed, and it'll be easier to just fill it in once. So that should work. Yeah. We don't need this scroll value thing anymore. Yeah, don't worry about this. I'm going to keep this stuff around in case we want to read some of it later, but I think it's not going to be very useful. Isn't there a way it marks the windows can snap and stick windows into place? Maybe. It's not bugging me that much. I do wish I had better window management generally, though. Like, I would love to do, like, half of this size and some other things, but yeah, it's not too bad. So in this case, I'm just going to... How do we want to do this? One of the things that we can still do that's nice here is use our screen brightness register here to basically make the screen like really dark here when we start processing, and then we'll make it really bright when we're done. And the nice thing about that is the nice thing about that is that then we'll see sort of how long stuff takes. So if we end up going over the frame, then that'll be nice. Nice to know. Because yeah, my guess is that we're going to end up still building this table as we're displaying the screen, which is not going to be too bad. Like if we're updating table entry 200 while the screen is displaying table entry 30, there's no problem there. And that's kind of the range of values that I'm expecting here. Where did I put that other one? Also, I actually don't want this to happen waiting for VBlank like this anymore. It's going to be fine for now, but I actually want to do that in... I want to do that properly after. Or move it into VBlank. In fact, why don't I just do that now? And I also think I'm just going to get rid of this stuff here because we don't need it. It's in Git. The only other thing here is that then we need to make sure to enable this interrupt. That should do it. And it didn't work because we should see the updated graphics here. Unless it did, but we never changed the scroll register, which I know we're not doing right now. So let's try that as well. Oh wait, that does it here. Okay, yeah, then we know that this didn't work. So we can, yeah, I just need to look up which one that is. Yeah, I've heard good things about Aquasnap, but yeah, we'll see. Oh yeah, I don't think I ever re-enabled interrupts. In fact, I think I explicitly had those disabled for this reason. That didn't work. No worries, guys. Also, we can do wait here, which is a good idea. Still not showing what I need to see, though. Also, this is something that I kept forgetting to do. We need to act the interrupt. By reading from 4210. But that still shouldn't make a difference because we still should have at least run this once. Why doesn't this work? Oh, really? Stream's cut out again. Oh, that's so annoying. Yeah, stream went down for a sec. Looks like it's back up, though. Sorry about that. It was happening a ton yesterday, too. I don't know why that is, but I'll have to look into that next couple days. It's definitely on my end, but I don't know what's causing it. I really don't know why this isn't working properly. Oh, that's why. I put it in the emulation vectors, not in the normal vectors. That would make sense. And this should work. Yep. All right, so now we got NMI again. And also, you'll notice none of the screen has been darkened. The screen will be dark for like some period up here if our processing goes outside of VBlank, which currently it's not. So we're going to just try to build this first table, and then we'll worry about that stuff. So I want to make everything 16-bit. Because that's going to be easier. Going to... Well, X will be our index register here. I think actually... I think I'm going to use Y as a counter here for now. We'll do 112 lines. And then we'll do decrement Y and branch if not equal to this. Let me shut off some other bandwidthy things here, just in case the stream doesn't drop again. All right, so what we're going to do is we're going to want 8-bit value in A, and then we're going to want to write some 16-bit values. So first we're going to do load A with 1, and we're going to store that in our scroll HTML table indexed with X. And then we're going to increment X. And then we're going to load 16-bit A. We're going to load a 16-bit value. In this case, how do we want to do this? You know what I'm actually going to do? Is we're instead going to do this. Compare X with... Hopefully the assembler will just know how to do that. Or yeah, we'll do this. And then we're going to do this last one here, where we're going to store 0 for the very last line, because that'll indicate the end of the table. But then we'll use x as our index, and then instead we'll use y as here. This here. And we'll use y as our scroll value. And then we can do ff like this. So the first one will be, oh yeah, then we actually don't need 16-bit A here at all. In fact, we'll do 8-bit A and 16-bit X and Y here. I hate having to manage that, to be honest. Yeah, we don't need to do this. And then we can store Y here. And then we'll decrement Y. And then we'll increment X twice. So all the time we're incrementing X by 3 every iteration, and then we'll have this. I think this makes sense. Also, we want to do this first because we need the run length before and then the value. Also, just that'll make it easier for me to think about. So I know the assembler will detect like which state it's in, or try to at least, and then it will give you errors if you try to load like the wrong size value. But yeah, it would be nice not to have to do that. Didn't like my store Y here. It's possible I'm not allowed to store Y indexed by X, but I hope that's not the case. Okay, so I can do it with the direct page index with X, but I can't otherwise. That's annoying. So then I'll have to go through A, which means I'll be changing sizes again. Do this here. It's just easier if I do it before. Actually, why don't I just change it here? Yeah. So now we actually want to fire off the HDMA for this channel, which shouldn't be too bad. In fact, I'll basically copy this first. Also, where was I sending this before? It was here. I actually don't think we have to do this here now. So if I don't do that, we'll get this, which is what I expected. Because I'm fairly certain that HDMA actually does run one extra, like the HDMA will actually run before every line. So it should actually be okay if I just run this here. Now we're actually going to want to use a separate channel than this one in case this one actually takes a while. So we'll do this. Offset all these registers. I think this is right for this. I'm not sure. I need to look this up. For now, everything's okay, just until we get it to work. File size is not going to be a problem. The original thing that inspired me to do this was 256 bytes, but I'm fairly certain he didn't care about that at first either, even if that was the end goal. Much easier to just make it work first and then deal with that stuff later. Yeah, as far as I know, you shouldn't actually need to set this stuff, like the amount, because that should be implicit in the table. We're going to want to set OE because we're going to do the scroll register here. And then we need the tables. All in bank 0 because it's operating at a RAM. So this may just work. Bam. That's so nice when that stuff just works. Cool. So now we're doing this right. We don't have to worry about timing woes. And it looks like building that table and firing it off was quite fast, which is nice. Also, I'm seeing an extra line at the bottom here, which I wouldn't have expected, but is probably okay because we have... I mean, if we're getting red here, we're only updating the first line of all the characters, so this is a really good sign now. That must be correct. So that's really nice. Let's go ahead and try to make this 224 a full size. And that also works. Very nice. And just for a test, I'll make it 223. See if we get the last line borked. And we do. Perfect. Then this is working exactly as we expect. Who knew that using the hardware like it was supposed to be used is actually kind of nice? Admittedly, one of the reasons I wanted to kind of not use the hardware like this yesterday is because one of the comments on one of the Elix demos was, oh, this all just looks like clever applications of the existing hardware. And that always kind of bugged me because I always thought, well, of course it is. Like, that's kind of the point. And you kind of have to play nicely with this hardware. But until yesterday, trying to do it that kind of way, I didn't really have the personal closure, the personal affirmation that, yeah, that was the right choice to not try and bork the hardware like this. Anyway, this is working. This is what we want. So now we want to build a couple other tables, which are going to actually do the writes. So this shouldn't be too terribly difficult. But we basically, so we want to have one of those that will actually be the address, and then we want to have the other one that's going to be the data. What I'm going to do first is, okay, we already have the tables here. I'm just going to hard code some writes here. Like, we're going to write to like the second char or something. But before I do that, actually, I want to set up the other tables because that's just going to be more or less copying this. In fact, we could do this in a loop if these were consecutive, which is probably what the other intro does. What do I call this? VRAM adder HTML table. So this is going to write to 1.6. 1.6 and 1.7 are going to be our addresses. And also we're going to want to increment the channel here. And then we're going to do the same thing with the data. Okay, it's going to write to 1.8. And then it's going to increment this again. And now we enable the HDMA. We want to enable channels 2, 3, and 4. So this should be E. Because that's, yeah, 8, 9, 10, 11, 12, 13, 14 is E. So we're good. And that way, again, we won't conflict with the other stuff. Now, if I just run this, probably weird stuff happens because we haven't actually set up the tables. Or we got lucky with the data in RAM, which is probably actually what happened there. So now I want to build these tables. The easiest one is going to be the first one, because if we're just going to hard code some data, actually they're both going to be easy in that case. But what we can do, we won't use LDY here. We're just going to hard code this, and we're going to do STZ here. I'm just going to store 0, so we're always going to write the first 2 bytes. That'll make this easy. And then we'll do the data, which will also be easy. Oops. Okay. The same thing here. Yeah, we can write 0 to that. Let's start with that, and we'll see. Okay, so now we have some dark screen here. So that means we took too long, which is exactly what I expected. So I'm very happy about that. So what we can do here is we can set up the HDMA to run before all of this, and then build the tables. And it should just work. It should work exactly as we expect, which is always nice. Because we're not using that much frame time, but we are using some of it. So now I want to actually change the data. So we write something interesting. So we can do LEA, something that'll give us some alternating bit patterns here. And then we should have gotten some bars, but we didn't. So why is that? Why would that be? Ah, you know what it is? Probably. I bet we haven't set up this right. We want to figure out the setup registers here. Here we go. So we want to write 2 bytes in the case of the address and data. We want to write 1 byte actually in the case of the scroll register. I think. Look that up again. Should be here. Yeah, we need to write twice to the scroll register. So actually we need to change this one, write 2 bytes at the same address here. So that's actually correct for 2 there. But then here we want to write 2 bytes. This and this plus 1 for the other one. So putting this to 1 should hopefully make this work. And it didn't. So our so 1 entry with 0 should be our address. And then 1 entry with some bit pattern should be our data. So here we don't need to set this for HDMA, which is good because we're not, I think. Or yeah, I don't need 5, 6, 7 here. We do need 2, 3, 4. Just gonna put in the table. Don't need these and don't need this. And 216 and 2117 should be our VRAM address, and then 2118 and 2119 are our right pointer here. So we had 2 here, and that was going to write our scroll register. If we did 4, the stretching should stop. If we did 8, who knows what will happen? Because we're not also writing the address. C should give us, should write the data, but we're not getting the scroll, so it probably doesn't work anyway. And +2 would be E. So this should be correct for this. Very odd. Let's just try writing a little dummy right here. I don't think this is going to matter because we're only going to write the one value anyway. So I think we'll be okay leaving that as is. I had that right bitmask there, didn't I? Yeah, I did. So this is what we should have gotten. Also shows that our stretching is working, but this is, or actually we should have gotten the opposite bit pattern. Which would have looked like this. This is what we're expecting to get. For example, if I write to, let's do this. That should give us the same results. It does. Let's say I did 32 bytes in, or I think it's 64 bytes in, which we write to over 2, don't we? That should work. Oops, STA here. And this should give us the second character. Yeah, like this. So if I write manually, it appears to work. So writing the 16-bit address into 2116 and then writing a 16-bit value into 2118 should just work. More or less regardless of this value, because I mean, could do this. Actually, well, what does that top bit do in 2115 again? Right, that controls when that's incremented. Which doesn't really make a difference in our case. If I change this to like 80, this should still work. I get the same thing. I'm gonna put this out here, and I'm gonna leave this here. All right, let me bump this up, I think. So this is, we're getting this here, and then from the HDMA we should get one over here. I'm not doing something stupid, am I? Like doing loading A and then doing STZ into the... Okay, I'm not good. Here's the other thing that bugs me. Even if it didn't work to set up these tables the first time, the next frames we should have at least gotten them. So it should have made sense. Hey, Drew, too. Yeah, this SNES thing was bugging me, and I don't have work today, so thought we'd do this. Does it just not work to do this via HDMI? Because that can't be. Because then how would the other effect work? And I have that bit mask right, don't I? Yep, that's correct. Because we use the 0 channel for the actual DMA. Where it resets the data. Which shouldn't actually matter because we enable the DMA here. And that will stall the CPU, so we shouldn't actually have to use that one. But I wonder if there's actually like issues with using like the top 3 channels. I wouldn't suspect that there would be. That seems weird. And actually there must not be because the scroll one is the first channel we use. And that works. So I don't think that's the issue. Yeah, also I wanted to remove the code that sets that up initially because we don't need that anymore. In fact, basically anything that touches 210E, we don't need. Thinking a little bit ahead to the 256B or something, but... Daniel Collins says, if you put the scroll on a different channel, does it still work? Good question. Let's try that. Let's remove these. And then we'll just do 02, right? So that should be the same as what we have now, basically. Yep, and then if we bump this to a different channel, and then we have this as is, this shouldn't work, right? And then if I change this to 4, that should do it. And there we go. So that seems to be working. I'll try also with 8, just to be rigorous. So that's what we expect. And then if I change all these to 3s, then this should work. And there we have this. So it's not that the HDMA isn't working, or that it's not working for certain channels. It's that the actual writes that we're trying to do with it aren't working for some reason. I meant rigorous with an I, but I'm sure rigorous with a Y would try something similar. So we know the bit mask is correct. We know at least this one works on other channels. Just to be cheeky, I'll do this, but I don't think that'll help. The bank here is fine because it was reading the data from the first one, and we know that this is mapped to 1F, so this should work as well. I can double check that actually. Yeah, here we have RAM mapped here, so that shouldn't be a problem. We're well within that range. Also, that proved that the scroll register thing worked. Well, all of this has, with us firing this off first and then filling in the tables. So that's good. At least that works as expected. Definitely putting 0 in the address. We're definitely putting something in the value slot here. Now, Colin says, it seems like 1, the table isn't filled correctly, or 2, DMA isn't started. Or we have the wrong addresses and stuff set up, but I don't think that's the case because this worked. One of the differences between these tables is we're using this different mode here for actually writing. So I can double check that again. Which is this 43x0, which is, yeah, this one. And in the scroll registers case, we write 2 to there, which is, wait a minute. Oh no, yeah, HDMA. So you write 2, which is going to write 2 bytes from the table to the same register twice, which is what we want for the scroll. Whereas for the VRAM updates, we want to do the byte and then the next byte. Yeah, read 2 bytes from the table entry and then write to this register and the register plus 1. I mean, we could try to use 2 here as well, but I think that's what I started with. And yeah, that doesn't help. One of the things... Another thing I could try is resetting. So let's not write the address. Let's just do the scroll and the data. So that'll be A here. because it'll be 8 and 2. And then here we can reset the address there. And then that didn't work either. I wonder if I can make these go to a different set of registers so I can make this visible. What are other registers that we have here? I could just mess with these data addresses. 2107 and 210B. I don't think the brightness is in the same range of registers. Or, oh no, that's 2100, isn't it? In that case, it should work. Let's try that. Put the data in there because that's going to be all zeros. Okay, so that appears to work. And you can see here is where we finished writing, and then we reset the brightness register, and then it was bright again until the HDMA reset it to 0. So that's actually really interesting that appeared to work like that. And it probably wrote 2101 as well. Which is, yeah, some sprite shit that we don't care about. So I'm going to set that back to 18. And then we can try doing the other one as well. Now, the other one may cause us some problems because it might actually, like, disable the screen. That seems to work as well. Not in the way that I would have expected, though. Oh, no, this is also always writing 0, isn't it? And then that is exactly what we would have expected. So the HDMA seems to be working then, which is bad. So then each one of these lanes appears to be working. It appears to be writing some data. But then why is it not updating VRAM? One of the things we could try is we could try uploading this data to color RAM instead and see if that helps. And then that should change that background color. That's 2.1 and 2.2. And that seemed to work. So generally, like, Higan and Vice and some other emulators tend to be really good nowadays. I generally trust the emulator quite a bit for these kind of details because these are the things that games are going to do all the time. So it really depends on what you're doing. Like, for really cycle-accurate timing routines, I trust some emulators more than others. But that's kind of not what this is. This is more just, like, setting up the hardware to do what we know a lot of games will already be doing. So in that case, I definitely trust this kind of emulator. And yeah, depending on the emulator, that also makes a big difference. So something This is annoying because it just worked for colors. And so we know it updates colors 0. Right, because we get the background color. Then that's the one that actually changes. What is happening on the right side of the screen here, by the way? Are we just getting... Yeah, okay, that's non-deterministic. So yeah, so then what this is showing is that the first HDMI lane is writing the address to color RAM. And it should be writing that twice. Or, hold up. Yeah, these are 1 byte values here. Let's set this up so that this writes the same byte twice. That didn't seem to work like I expected. Because if we were going to write to 2 bytes to this data, so what I'm trying to figure out here, we wrote 0 into the address, and then we're going to write 2 zeros into here. Which should have been setting it up like this, I think. But we only... Why is this green then? Oh, yeah, of course, because we're writing our AA bit pattern, aren't we? I was thinking we were writing 0 to this. So then it's actually weird that that when we wrote the screen register, that we got zeros here. When the bit pattern for the data was this. So what if we did OFOF, which should give us full brightness, right? And we did like 08. Actually, whatever we put over here should be fine, because that's the second value. Right, so if we do OF00, okay, something's weird here. So this should be a little ending value, and it stores it here. This should be set up to write the first value to this, and the second value to this plus 1. Oh, wait, no. That should have given us full brightness. Okay, yeah. I had the notation wrong here. Little endian, still, this is going to be the least significant byte, but it's going to be stored first, so that's going to be written in the screen register. So if we do 0008 here, and this is writing a 16-bit value, then we will get half brightness here, which is what we get. So that's expected. So then this is working. And this, depending on the bit patterns here, we'll get like different brightnesses due to because we're writing to this register. So it looks like the data here is being written correctly. And that bugs me. So then why can't we get into VRAM? One thing we could try Dear asked about the right CPU mode. I'm pretty sure, because this was writing the right values that we expected. The 16-bit we write here, and then we set it back to 8-bit here. So it should be fine. Because we're 8-bit coming in with 16-bit index registers, but that's fine because we're only affecting A here. I think this is okay, and this should be the same. So that we always write 0 here to the address. Another thing that I could try here, when all this is done, we can do a dummy right here without writing to the address. Wait a minute. Right, okay, that makes sense. So what if... So after I reset the screen brightness, what if I just wrote to this value here from this? Now, this probably doesn't work because I think we're locked out of VRAM there. Yeah, no, I don't think that was a good test, actually. I was hoping to see that if we had the HDMA set up the value to VRAM, that then we could write this, but I don't think that's going to work like that. Hey, Ratchet. So, So when we write this, the data looks correct, and when we write it to any other addresses here, it appears to work, and that's very frustrating. So this is always writing 0 to the screen brightness, because that's what our addresses are, and our data is that alternating bit pattern. And if we write that, then we always get this. We should even be able to do both to the same one. And then we'll get this, they'll both happen in VBlank, so the second one should win out. So then we even see the ordering works. Because if we turn off this higher channel here, whoops, which is 6, 2 and 4, then we'll get black. Okay. We also don't have to build these as separate tables. But I would kind of rather merge them once we know that this works. Try something here. Hey, W23. My modem's in the other room. I'll have a look at it later. Sorry about that, guys. So one of the only things I can think of here is that for some reason writing to VRAM, like we get locked out before we actually get a chance to do the write. So one of the things I think I want to try here is rearranging these tables a little, or rearranging which one we're using here. So we'll make the address the first one, the data the second channel, and the scroll the third channel. And make this 7. That didn't help either. There's definitely priority between the channels. My understanding is that the lower channels take priority. I can find that. Actually, let me see if this has anything. So I'm already doing a DMA to put the video memory, or to put the data into video memory, which is normal DMA. So that's up here. In fact, that's actually in VBlank. With this here when it uploads the characters. So we're already doing DMA to 1.8 here, which is what we expect. Actually, this one. Lower ACMA channels have a high priority. That is if you have two tables running at the same time. Palette index will be set before the palette value. And there it's even using it to do the color like we saw before. Something's weird here. I found a source that says that games were doing normal DMA in an IRQ to update VRAM, which I also couldn't get to work. So I wonder if there's something else I'm missing here. My old code just looks like this code does, as far as I remember. Double check, but then I wasn't doing any HDMA outside of VBlank, so it should be the same. Here's my old code. Yeah, here we just set up the same stuff. current adder, which was 16-bit here, so that's why this is done. I even had the transfer mode in the data stream. So on Game Boy Color, it appears that people are doing this. I'm actually struggling to find any information about this. Most of the tutorials and stuff don't really cover the fine-grained details. It's here's how you do DMA into memory. Here's how you load a palette. Not the most helpful thing in this case. The most frustrating thing about this, though, is that it totally worked when writing to other registers. That I don't like. And we need to set both, because if we're going to write different addresses here, or do we? This is interesting. That in this case we could write 4 bytes to 4 consecutive registers, which means that we could sort of interleave the address and data parts of this table. I don't know if that helps, but I'm willing to kind of give it a shot just to see. And then we can kind of bake both of these into one channel, which is nice. This will make our table bigger, but I'm willing to give it a shot. All right, 7 here. No, that's not 7. That's 4. Into 1-6. Then we'll write 1-6, 1-7, 1-8, and 1-9. Which is exactly what we want to do. Yeah, so we just have... This actually will make the total data smaller for all the tables. But yeah, here's our address, and then here's our data. This will actually be more convenient if we can get this to work anyway, because of the... Oops. Yeah, there we go. Because then we can update both in... Like, I think it'll make the addressing more convenient. Maybe it won't, but I think it will. Still didn't work. Also, we are enabling more channels than we would need here. Just going to reorder these to stay in the same order as the channels. Again, if I dump 0, 0 into here, we should at least get some funky stuff. Yeah, so then this is just going to be writing the background color OIM and then data for accessing OIM. So should be safe to drop that to channel 2. Whoops. Whoa, what? Why is the scroll thing down here now? Oh, it's because we never initialized that, so that actually could be anything now. Yeah, so that's down here. Yeah, so without that channel, we'll actually just get crap, which is okay. Again, ensuring that the scroll channel works. But here I'm trying to write to color memory now. See if that will help. I don't think it will. Because we need to change the mode to this one. It's going to be 3. And then we'll at least get a different color out. Because it'll write the address twice, and then it'll write the same data byte twice. Or it'll write the data 2 times. So if we change... this was 00, which makes sense. Actually, I want to change that to 1, just because I want to try that. And then it shouldn't update the background color, but it did? No, because it wrote the address twice, right? So then this will not update the background color. And then we'll be changing some other color, which we can't. Actually, we should be able to verify because we'll get the whatever value is in that we wrote here. And basically, I think we'll get the third palette address there. So if we do 3 like this, then we should change the greenish color on these lines instead of the background color. Because it wrote this address, and then it wrote this address, and then it wrote this value twice. Low byte and then high. So if we do like 1F00, then I think that'll change that all to red, which make it disappear. Or, yeah, brighter red. So again, what this is showing is that with that 4-byte table, I think the... Like if we change this to 0 again, then we should get brighter red in the background, which a bit hard to tell, but I think we do there. So what I think this is showing, unfortunately, is that we're getting good data out of these tables. But for some reason, when I point it at the VRAM addresses, for updating the address and then writing the data, we just get nothing. That's the only change. That's frustrating. This SMW Central site is just a blast from the past. I was on so many forums back in like 2002, 2003 that looked like this. So in a way, I find it really charming, but boy, is this awful looking. I'm just going to grab this regs document. Yeah, it's a good register name. You know what I kind of want to do? I kind of want to just put a bunch of values in here and see what happens. A bunch of different values. So then we get some proper copper bars here. So again, this is the same table. And we are actually writing different values to it. But this loads into the color registers now. And this looks exactly like it should. Because we're filling up the red channel many times and then the green channel fills up over time. With sort of the low and the high bytes here. So that makes a lot of sense. But it was this one that we wanted, which will, yeah, mess this stuff up. Oh, wait a minute. What happened here? That can't be what I think is going on. What are these other registers up here? 2 and 2, 3. Yeah, okay, yeah, that's enabling and disabling the window mask. So that makes sense why we would get those cutouts. So again, that just shows that this is writing 4 registers in a way that we would expect. But for some reason, we're not getting any VRAM writes. Unless... Oh, this better not be the increment stuff. I don't think it would be, because then we... This better not be what I'm thinking it might be. No, because it shouldn't... The increment shouldn't matter. Because we would have gotten the increment after the first write, which means at least the first byte would have gotten through. And we particularly set the address. I mean, so ideally we should put 80 into there. Into 2115, which we do here. That's what we do for our dummy write as well. I mean, even without this, I would have expected at least our first write to get through. We don't touch it after that. Although, actually, I think we want this there, but that's something else. And this dummy right should still basically work as expected. And it does. In fact, even if I do this, then we should get the same results. And a slightly different color without one of these. Oops. Yeah. Try this with the address as well. Nothing. Why? Because how else are we supposed to update the VRAM every line? We only have to update like 1 byte. And 2 should be perfectly safe. In fact, actually, we do have to update 2 because it's 2-bit planes. So we definitely have to update 2 bytes. And we have to do it at different addresses. So I can't really think of any other way that would be friendly to the hardware than to do HDMA like this. What if we don't clear the data at the beginning of the frame? Well, then it's not cleared, so I can't tell if this is correct at all. And I don't think it is, because we should have at least had some recognizable pattern. We could try moving all of this stuff outside of here. And clear it here. And then we get the same thing, which is not fun. So we'll rule that out. So we're we're definitely accessing these in the same way. In fact, we could even, because we're doing 4 writes. This basically is a pretty accurate simulation of what we're doing here. Right, the 4 bytes like this. Usurper Tungsten, thanks for the follow. Yeah, that Grog's Guide is, that's what I'm looking at here. I did find the no cache docs here. Accessing during H-blank doesn't seem to work too well. It is possible to change palette entries during H-blank, but it seems to work only during a few clock cycles, not during the full H-blank period. That may not be HDMA, but because here's the thing about that note is that I'm actually guessing that that's going to pertain to trying to do that from the CPU. But we'll see. Hey, Middle Voids. Yeah. Get to watch me be frustrated 2 days this weekend. Ugh. Here's the other frustrating part, is we know this routine here that uses normal DMA bangs on 1.8 and 1.9 after setting this, which should be fine. What are our modes here again? Let's see if we change this to do 1.8 and 3 here, and then we'll just be banging on these addresses. Like, we should at least see something if this is writing at all, because then it will just internally increment that pointer all the time. But it really bugs me that that's not getting through. If you do this at 2.2, this should change a bunch of the palette colors. Didn't like that. There's even an example here again. It's using HDMA to do the colors. Oh, this is so frustrating. can't imagine it would be something stupid like the mode determines whether or not we could do this. But just to try something else. Change the graphics mode. I'm guessing that didn't work. In fact, if we had a clear VRAM thing here. Did I remove the dummy right? I think I did. So there's our dummy right, although we expect to get our other stuff here. Oh, I didn't know that on the Amiga, that you had to like enable a bit to enable access to the, or to allow the copper to start the blitter. That's annoying. A can in the background. Yeah, I do awful stuff in my free time, like sit at my coffee table and drink Coke. So scandalous. I wonder if I just search SNES VRAM access, if that helps at all. I don't think so. I don't think there's memory view or anything. I could try a different emulator and see if I can look that up. I think it was the no cache one was supposed to be pretty good. I mean, I might as well give that a shot. Let me just see. Where did that go? There it is. Let's just see. All right, so this is in no cache. And it also doesn't work, which is a good sign. Or, well, you know. Let me set this up in my path so I can do this quicker. Then I'll reload my terminal. Okay, so I can start that up. That's cool. Of like Semtex. I gotta try ASM1 at some point just to get that experience. I tried TASM for C64, but I was not a fan. I probably wouldn't be a fan of ASM1 either, but you know. All right, let's just try. Gotta escape this. Or not. Or is it that in make? Okay, apparently it's supposed to be this. That's not playing nicely. I'll just rename it. And that's just going to be how that works. Although now it doesn't seem to load properly. I wonder if it's because of this. I'm getting two spaces there. Ugh. Wow, okay. So now I can't even get this to start. So I had to drag it onto the executable, but at least I can kind of dig around in here. here's the actual debugger. Particularly, you can see the tiles. So this is cool because we can see which tile is here, which is what we expected here, because like every fourth tile I'm doing this, and we get the first data here. This is the screen with BG1 has this tile here, which makes sense because we're using the raster tricks to actually do the stretching. Other backgrounds aren't enabled. We're not using any sprites, and here's the palette, which is the 4 colors we set. Oh, I'm so annoyed at this. I wonder why I can't get the start from command line. I'm going to fix that first. I wonder if it's just because I need like an absolute path or something. Oh, white counter? I didn't see that. Oh yeah, here it is. Yeah, that's what you're saying. Yeah, absolutely. Yeah, right at the beginning of the memory there. In fact, we can look at our tables as well. Not the most comfortable viewer here, but this is... Yeah, 1 and then 1, 2, 3, 4 bytes. 1, 1, 2, 3, 4 bytes. Looks perfect. And then down here, we'll have 0 at the end. 1, 1, 2, 3, 4 bytes. Wait a minute. Why am I getting 2 zeros here? Oh, it's just probably because this is probably uninitialized. If we look at the data layout. Yeah. Data layout's like this. And so this is probably just uninitialized, and then we only overwrote the first one. And before that, here's our scroll addresses. And then, yeah, there was our counter at the beginning. Yeah, so this is nice, but I want to get this working from command line because that really bugged me. That didn't work. Not entirely sure why. Okay. So I have to escape this because of bash, and then I have to do this. Fine. Then I can get it to at least start the emulator, but it doesn't start with the ROM here. So I wonder if I can do like this. Go to full path. That didn't seem to work either. Ugh. It's probably because it's giving it Unix directories. That sucks. I can't run it properly like that. Let me see if I can at least do it from the other command window. That would at least be easier than dragging it. Oh, I hate the Windows terminal. Command line sucks. Yeah, so I just cannot get any of these to start from the command line, which is really annoying. But this will probably be helpful anyway. Put all this back. At least this still works with this. Looks like this shows the help screen, but it just says switches and then this name, run name. Didn't seem to help very much. Maybe if I do it like this. Let's do no escape. Right? So that'll run it. And then instead of the demo here, let's do the full path. No, that still doesn't work. Just in case. Wow, okay. Oh, what a disappointment. But at least it worked. Ugh, that's awful. Oh, and these are really weird. What the hell? What is this? What the hell is this notation? This is so weird. Okay, at least then we have the regular notation. Yeah, so here's waiting for the interrupt. Eventually it'll start the transfers, but I don't, other than viewing the VRAM, I don't really know how we could debug this. There's an IO map. That looks useful. In fact, that might be really useful because then we could at least see if these registers are changing. I would imagine. this is the status. $2180. What is that? Ugh. My connection is ridiculous. This has not been my most frustrating experience with this kind of stuff. Definitely not my least, though. Yeah, sorry guys, stream went down again. I'm so sick of that happening right now. Setting up a reminder for me to call my billing manager and ISP tomorrow. Anyway, this 2180 is actually a port to access WRAM, not VRAM, which makes sense. Oh, this is a very... Man, nothing about this is comfortable. Okay, at least I can have breakpoints here. Like, let's say I put a breakpoint here. Okay, so now I have a breakpoint before this. And I wanted to see these addresses. So this is before this DMA runs. This should be the DMA to like clear the data. Oh no, this 81 is the port control, I think. I think that's what this is. Hey, Ashmedai. So I want to see if any of these change here. If we run to the next one, which is going to be F3 on the next line. Yeah, now at least we have a different address here. So that was at least getting written. And eventually... Now I have A0, but that's because I think we did that dummy right. I think that's why that happened. Now if I step past this, this shouldn't change. In fact, if I hold on this is building the tables. Building more tables. I'm gonna sit here and wait. Now if it's just me, or did this change? Where's our... So this is the beginning of our interrupt. If I jump in there, we're at 20 here. It's gonna clear our I want to say frame buffer, but you know, line buffer, I guess. Yeah, and here we reset the address because we're going to run the DMA. And then that's where the DMA runs. And then we have this here. And then we've set it to 80 because we're going to write to here, the port, which does our dummy write. Yes, metal voids, that is weird. Not going to be a very good benchmark, I think. This is kind of cool how it's setting the DMA registers here. It's weird that these don't change there. I'll split these up again just to try and eliminate some variables here. In fact, actually, let's increase this one. Yeah, so now we have here, this is our regular DMA that we're using to upload the characters. And then the other channels that we use to here upload the data, which isn't working. And here upload the scroll registers, which definitely works. This is all we want to see. Is this happen here? I'm actually tempted to start looking into some emulator code for HDMA to see if we're not allowed to do this. I'm going to do that. Yeah, I'm indeed staring at tiny, tiny windows. I was staring at much nicer scaled things earlier, but they didn't work, so I'm stuck with staring at tiny stuff. So here's some open core plugin with Higan. All I really care about is that we can find some HDMA stuff in here. Now, I have no idea how this code is laid out. Let's just try searching for HDMA. Okay, so it looks like it's in the DMA stuff. HDMA run. Maybe interesting. Looks like it's going to be in here. Okay, so it looks like it gets these callbacks to tell it when it's entering different states. And it uses its own pending thing. Yeah, probably DMA run is called periodically. And pending will probably actually do the work. Yeah, if it's pending here. And then it'll call its own exec method here. But this just looks like it's doing basic moving, which is nice. So I don't think that's where we're going to find this stuff. Oh, that's in GBA as well. That's kind of funny. I forgot that that would be the same. But we can do SFC. See if DMA is here as well. And it's probably going to look a lot the same. Oh yeah, it's going to block out WRAM to WRAM. I'm guessing we'll either, if like we're not allowed to do this, we're either going to find some code here that locks us out or some code in the PPU that locks us out. Which is probably going to lock us out regardless of whether it's HDMA or DMA or whatever. Yeah, nothing in here. Yeah, I can log if I can build it, but okay, so this is just going to be some top level stuff that's running this. Looks like. MMIO will probably help at least, because then we'll at least get the VRAM address. Okay. That's annoying as hell. I'm guessing the debugger is just going to tell the debugger that this write happened. But what I'm seeing here is if the display is disabled or the vertical counter is greater than, depending on overscan, 225 or 240, then it'll let us write, which mentions nothing about yeah, nothing about the other stuff. So that's terribly annoying. You can only write if the display is disabled or if the vertical counter is here, which is basically in VBlank. Only update inside VBlank, yeah, that's what it looks like. Which, there goes this plan. That's pretty annoying because I didn't see, like, I saw mixed messages all over the place saying that we could or couldn't do this, saying that usually people didn't do this, or usually people did DMA to do this. But according to this, that's pretty frustrating. Let me just see. It looks like here's the actual register interfaces themselves. And here we go. So yeah, this just goes through that VRAM read thing here. VRAM read and VRAM write, which is exactly what we were looking at up there, I think. Yep. That is terribly annoying. Hold up. So you can have up to... I would be so mad if this is the way he did it. But you can have up to 32 sprites active on the same line. I'm gonna run this in the debugger, and we're gonna see at least what it looks like here. Not necessarily how they're doing it, because it was kind of a goal of mine to not disassemble this too much. But I've tried a good deal of things now. So I'm not gonna feel that bad at this point. No, I totally don't have this ROM on my desktop right now. All right, so here we have this in the debugger. Okay. There it is. It's sprites. You know what? You know what I remember now? Oh, I totally forgot about this. Oh, this is so frustrating. There's totally a hardware trick on SNES you can use that'll just repeat the sprites over and over again. Like with this, it'll basically give you this hardware trick. Why is this going nuts though? Why do I remember a trick like this? All these are pointing to the same OAM stuff here, and all the locations at the top left. But then, oh, this is just showing the screen, isn't it? This is not necessarily showing the sprites. So yeah, so maybe they aren't doing it that way. This is just trying to show us the screen to show where the sprites are, and then we're getting this flickering because they're all just pointing at the same place, which would make sense. Okay, it's using mode 7, and I don't know why. So yeah, I actually don't think this is being drawn with sprites at all. I think it was just I was just being confused by this view because it was showing me this. But I think this is just showing me the screen so that it could show me where all the sprites are, and those are all just pointing at nothing basically. Um, Also, their tile address is all 0, so that tile is clearly being updated. Or actually, here it looks like we have a bunch of these bit patterns. In fact, that's exactly what we're seeing here. These are just bit patterns in the tiles. Why is this showing BG1 and BG2 if the screen were in mode 7, though? Maybe I'm reading that wrong. This does say 7 here. Yeah, it's quite possible the tiles are just generated like that and then selected somehow. I'm not sure. This is completely different than what I thought, though, I think. I'm also really not sure how to read this debugger stuff. So those look to be pretty static. Yet the 8-bit per pixel ones change. So maybe the first couple bits of these are static and then other ones up, and then the other bits updated or something. Very odd. Also interesting is how the palettes are changing ridiculously fast like this. Which I saw over here as well. Because the, oh, where was it? The color memory address is changing wildly. Yeah, mode 7 is a 2D affine matrix. So it's you have like a pixel pointer at the start and then it will add that every pixel, and yeah. Um I'm trying to find in this window where it would show those matrix values, but I don't think that that's what's happening here. I could be wrong, but like this doesn't look like that kind of stretching to me. This turned out to be really frustrating. Yeah, all these backgrounds are going to be disabled, especially if it's mode 7, because you're only going to have the background and the sprites. Sprites don't appear to be doing anything. It looks like the tiles just increase linearly. Or actually, wait a minute. Most of where I'm hovering doesn't show anything. The tile addresses that ends up being 0, and we have tile number and attribute as well. Down here we start, if I go down here, we get like 65, 66. Along the left side of the screen there. It'd be funny if he was using mode 7 to rotate the screen sideways. Just because I'm not seeing any other part of the tile map that's being used than just that left side, just hovering over here. I can't imagine why that would help though. Let me look up the addresses for the mode 7 thing again. So 211A through like 211F. So if I can try to find those here. Yeah, if you do that, you have or you have long lines in X to fill, which might be easier, but then again, the tile data isn't changing, except for some reason these are, but that might just be the color memory changing. It'd be pretty annoying if this effect were done just with color cycling, if that was the only thing actually changing here. It's possible, but it'd be pretty annoying. But I wanna find those addresses. Another one of the really nice things, though, another one of the nice things about using mode 7, though, is you have 8 bits per pixel. So the filling would almost be easier if that's what you're doing, but I don't think the map changes either, because it seems to be pretty stable. Yeah, that's a good point. I could probably see in here. Just hoping I can see. Okay, this is... Oops, I'm in bank 1. I'm not that interested in making Raycaster do it all gaming. Man, there's really not a very easy way for me to scroll to where I need to go in this window. I can increase the resolution here. I gotta be honest, do it all gaming. I can't tell if you're trolling me or not. Things you're saying are pretty out of context. But I don't think we're gonna see the registers here. Yeah, it would have been around here. So I don't think that is gonna work. It's so weird that they wouldn't be here. They should be in here somewhere. We do have... Because we have the scroll registers here. It's not these. What do you mean these? I figured this would be the... I thought this was another memory view. Most likely the stack. But I could be wrong there. What is that? Oh yeah. Toggle CPUs. That's funny. Oh, they're right here. These are the registers here. Wish I could change those via this interface. One F and 2-0. This is our center point, which is 7F. 7F is 127. 127. Fortunately, this is like overlapping. I want to see which register is which of that matrix because I don't remember. If I can, where did I have this? Okay, so here I have this. Yeah, it's probably possible for me to disassemble and reassemble it, but BCDE. Here we go. Let me, I have some code to calculate the identity matrix for this, because I don't even know what I would set these to, even if I disassembled it. So default value. Hold up. This is the F# code I did for the actual matrices. So the default matrix would just be this. Rotation 0, scale 1, scale 1. So A in that case would be 1 times 256. B would be 0, C would be 0, and D would be 1. Or 256 in that case. But I'm seeing 0, 256, probably negative of the same, which would make sense in this, which means this is rotated. In fact, this is rotated. Not entirely sure which way. Yeah, it's definitely rotated 90 degrees, which is what I suspected. If I go to the very top of memory, or at least the top of the first bank. Oh, this viewer is terrible. From here. Let's just try this. Our number of bytes, we know it's 256 bytes. Let's store this somewhere. Yeah, and all this shouldn't matter. It looks like it wrapped around. And at the top, actually we want the RTI. Whoops. This is gonna be cheeky as hell. Only problem with this is I'm guessing all these numbers are hex. Were there labels in there? I don't think there were labels. I think there was just disassembly. Or just the addresses and the bytes. I don't think... I mean, it shouldn't matter because we can just do hard-coded addresses like this. We shouldn't need them. It would be more convenient with them, I guess, but... I'm just going to do this by hand. It's not going to be that many. I mean, again, this is all just because the ways that I did it made some incorrect assumptions about being able to update VRAM during H-blank. And since we can't do that, I just kind of want to see a bit about how this one's doing it. I don't really care that much about knowing exactly how it works if it ends up being fairly complex. But it's just annoying to leave empty-handed, as it were. Did I mark some of these A's? I hope I didn't. Like this one. Because that's going to be referring to the register, not a value, most likely. I definitely don't want to spend the rest of my day off reverse engineering someone else's code. But would be interesting to see this not rotated at least. Actually the easiest way to see if it uses DMA is 420C or 420D. Okay, so it's using HDMA, which I also didn't expect. Daniel, no, that's what Thursdays are for. Yeah, exactly. Or did I have that? Is that the right one? Oh no, it's 420B and 420C. Yes, it's not using DMA. We should see 2116 or 2117 in here at least then. Do we not? Really? That's surprising. I don't think it's going to be as simple as just taking the way another system do it and plugging into these registers. That's more or less what I tried to do initially, and that very much did not work. Trying to use that kind of technique. Let's just see if I can assemble this. Yes, again, guys, it's not going to matter if we have another example of how to do it on another machine, because this is doing some weird stuff, I'm going to tell you right now. UR value at the beginning looked quite big. I think this is a 0 page address because it's not an immediate value. That's the difference. That's the difference between the hash and not having the hash here. Line 5, yeah, this is big. But it might be crap. In fact, it looked like this was some other thing that, like the disassembler, there were some extra bytes here and the disassembler got out of sync, which shouldn't matter because as long as the rest of this is correct, even if the code is not exactly what we'd be seeing, as long as it, yeah, it probably is the sign table actually, now that you mention it. Yeah, we're probably just seeing disassembly of crap there. In fact, here we see CLC and XCE, and these start to look normal. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. Yeah, so somewhere around here, it actually starts turning into actual code. But it should be fine, because if we assembled this, we should get the same sequence of bytes that we would have gotten otherwise. So yeah, that must be the sign table, which I know from looking at this in a hex editor, it looked like that was the case. So let's just try this. May have to inject some other stuff here to get this to actually assemble properly, but we'll see. Just for hacking this together. Oh, it didn't like that this was out of 8-bit range. One of the things I might be able to do, though, where were those registers? Yeah, so this is not going to be that straightforward to assemble, I think. I guess I could rip out the binary of the thing and put that there, and then do ink bin here, and then put this in all in the right place. But I'm getting definitely to the end of what I wanted to do with this project here, which is try and recreate this in a way that I thought would have been sensible, but I guess it wasn't. And I'm more at a point where I'd rather just admit defeat here, especially seeing that the original one that inspired me to do this clearly does not work, at least how I expected it to. I mean, even just the fact that it's using mode 7, that it's rotated, kind of changes the game a bit. So, yeah. Anyway, I mean, I put in a good run, I think, trying a lot of different tricks. And in the end, we found out that doing a raster trick and then changing the graphics every line is at least not how this one works. So I'm going to commit what I have, just because. I think so. My goal with this was to so I saw this effect, I saw it working, so I thought, okay, I know how I would do this on another platform. Let's try that here. And now after trying it, didn't really work. And then after we saw this other one running in the debugger, we could see that it was using mode 7. That it's actually done sideways. I could sit here and reverse engineer this more, but I kind of don't want to do that because my goal with this was to kind of have a fun little project that I could do in a couple days. And it looks like that's not going to be the case because now we've already spent those couple days. So I'm going to call it quits on this for now. And then maybe I will, if like I'm gonna hop on IRC, and if I can see this guy in there, then I'll ask him how he did it, and I can like report the findings, I guess. But at this point, I don't want to sit here reverse engineering this because I've got some other projects I'd rather work on. But I thought this was a good run. If nothing else, I learned many ways not to do this on SNES. And yeah. So yeah, this was fun, but I think that's where I call it quits. Anyway, thanks for hanging out, guys. I'm gonna go ahead and shut this down, and I'll call my building whatever. See if I can look into my internet and why it's cutting out because that was pretty annoying this weekend. But anyway, I'll see you guys later.